another piece of information we can get from the orbitals would be the spectral lines for the atom. Okay, we've talked about this before. If you know the allowed energies, then you know what sort of spectral lines you can expect from your atom or not expect from the atom, because if you remember the Bohr frequency condition, the energy of any photon that will be absorbed or released by the atom must correspond to a difference between allowed energy levels. Okay, so difference between allowed energy levels is delta E would be hc over lambda. Since not every possible value of delta E is possible, not every value of lambda can be observed. So there's only specific wavelengths that you can observe in your emission or absorption spectrum. What is the energy of a photon released when the electron in a 3p orbital of hydrogen loses energy and ends up in a 2s orbital? So you have an electron going from the 3p to the 2s. Okay, so your delta E for the electron is energy at the 3p level minus energy at the 2s level. So this is negative 13.6 over 3 squared, which is 9. That's E for the 3p, and E for the 2s is negative 13.6 electron volts over 2 squared. 2 squared is 4. And if you did that, you'll find the energy of the photon must be 1.89 electron volts, and you simply change that to joules. An electron volt is 1.602 times 10 to the negative 19 joules, so that gives you a photon energy of 3.03 times 10 to the negative 19. So equate that to hc over lambda, the Bohr frequency condition, and you can solve for lambda. It's just hc, so you rearrange this, hc divided by E photon, that gives you your lambda, and you'll find, if you did the calculation right, it's going to be around 656 nanometers, and so that would be red light.